Hello guys, welcome in this video. In this video, we are going to talk about the time step. The time step or the delta T is a very important definition in Houdini simulations. It's the time unit that is used in the simulations. So in Houdini, we simulate frame by frame. So from frame 1 to 2 to 3 and etc. The time step is just the time between two successive frames. So for example, the time between frame 1 and frame 2, this is our time step. Before we go intuitively and explain the definition of the time step, let me write the formula of updating the velocity in each frame, for example, by the forces. So if we want to update our velocity with a force, and I will talk about this now, we will use this formula. Let me break down this. If we have in our simulation an external force, any external force that is affecting our velocity field, so it affects, for example, if it's a smoke simulation, it affects how the smoke behaves. Okay, the velocity is the direction and the speed. So for example, if we have a smoke simulation that is moving upwards, so we have our velocity mainly upwards here, like this, and we have an external force affecting our velocity field like this, for example, it will affect the shape and the behavior of our smoke. So when we want to update the velocity or affect our velocity with this external force, we are not just going to add the force to our velocity. Okay, so here the v nu or the velocity nu is the updated velocity, okay, of the current frame. So if, for example, if we are in frame 4, we are going to take the old velocity, which is the velocity coming from the previous frame, which is frame 3, and then we are going to update it with the force, with this force, but we are going to multiply our force by the time step. So so to recap, if we want to update the velocity of the current frame, we take the velocity of the previous frame and add to it the force with this formula here. So this is what happens. This is when we have a force and we want to apply this force to our velocity. We want our velocity to be affected by this force. For example, this force can be gravity, it can be any noisy force, can be a custom force that we make, and we are going to use this formula. Okay, we are going to update the velocity, the current velocity, by taking the velocity of the previous frame and add to it the force multiplied by the time step. And I think we now jumped a step forward. We need to know what this force means and the time step. To break things simply, if we have, for example, a car that is moving, and imagine that this is a car, and we have an external force pushing this car forward. Okay, so it keeps moving forward, So now this force will affect the car velocity and will make it move forward. So why do we use this formula? Why do we multiply by the time step or the delta T? Why do we do this? Simply imagine that this force keeps pushing your car for 10 seconds, and when 10 seconds pass, when 10 seconds pass, your car becomes at this position, for example. Okay, imagine that here we had 10 seconds. But if we see, or if we assess the position of the car when if we assess the position of the car when 5 seconds only pass, 5 seconds only pass, the car will be in the middle. Okay, so here only after 5 seconds. So this is why we are using our time here, because in Houdini we are simulating frame by frame. So for example, from frame 1 to frame 2, if we set our time step or the duration between these two frames to 10 seconds, our car is going to be at this position. So the time here makes things different. But if it's only 5 seconds, the car is in the half, and the same thing applies to the smoke simulations and any kind of simulation in Houdini. Okay, so if we are simulating frame by frame, we want to define how much time how much time do we have between the two successive frames, because sometimes we can set this time to be big and this time to be small, and this will affect our simulation as you said here. So the less time you'll have, the less of this multiplication. For example, if the delta t is 10, okay, and 10 multiplied by your force will make your force big, and it will move your car forward like this. But if it's only 5, as I said here, when you multiply it by the force, it's going to be less. Okay, this part is going to be less, and it will be added to the velocity, so it will move the car here to the middle of the way. So this is a time step. We need to define the duration between each frame in Houdini, because this will affect our simulation. Okay, and of course, if you set the time step or the duration between the two successive frames to be less, okay, you will have your simulation computed each 0.2 seconds. So if you compute frame by frame, so from frame 1 to frame 2, Houdini regards this as 0.2 seconds. So imagine that you have a complex smoke simulation, for example, and you are computing the velocity and all of the fields every 0.2 seconds, and this surely will make your simulation be more accurate than, for example, a delta t or a time step of 10 seconds, because you are computing things every 0.2 seconds, and this will make Houdini capture more details. Okay, so this formula here is called the Euler formula, but it's very, very easy now, and we understand it intuitively, and we understand why we want to take time into consideration. So the time step in Houdini is by default 1/24. Okay, and this is the default time step. But why? Because in Houdini there is something called frame per second, or FPS. And this FPS in Houdini is 24. So in Houdini, when it simulates 24 frames, this is regarded 1 second. Okay, so after the frame 24, you will have your 1 second of the real time, after 24 frames, you will have 1 second of real time passed, okay? So if we have 24 frames per second, and this is the rate set by default in Houdini, if we want to get how many seconds in one frame, we will divide 1 over this frame per second, 1 over the FPS, which is 1 over 24. So our delta t in Houdini is by default 1 over 24, okay? And this means that Houdini regards 24 frames as 1 second. So when we are applying any force in Houdini, we are going to multiply it by the time step, which is 1 over 24 before we add it to the velocity, because we want to take the time into consideration as we said. Let's make things more complicated. Let me change the color, for example. What if we say that we want to divide the duration between the two successive frames into, for example, 3 durations? So from frame 1 to frame 2, here we had delta t of time. We want to divide this duration into 3 durations, or 3 delta t's, okay? And this surely will make the simulation better. If, as we said, if you are computing the velocity and all of the fields in lesser durations, like here, you are going to have more accurate results because you are going to capture more details. Actually, simulations are just numerical estimations, so they are not 100% accurate. You are just trying to solve things numerically and solve the equations and all of the complex stuff numerically, and you are just estimating the result. So if you are estimating the result every 0.1 second, it will be more accurate than if you estimate the result every 10 seconds, okay? So if we want to divide the time step into 3 time steps, or divide the duration between the 2 frames into 3 durations, we can call this substeps. So instead of simulating from frame 1 to frame 2 only one time, we are sort of simulating from 1 to 1.33, then 1.66, then 2. Okay, we here have 3 durations. We simulated it, or we computed things here, and then things here, and then the third time here. So now our delta t, our whole delta t between the 2 frames here, if we are going to use 3 substeps, our delta t should be divided by 3. So here we have our delta t by 3, or our old delta t by 3, and delta t by 3, and delta t by 3. So now, to incorporate this here in the formula, if we want to compute the new delta t in each substep here, we should divide, or sorry, we should here multiply our frame per second by our substeps. It's sort of dividing the delta t by the substeps, and this is very intuitive, okay? And also we can make the user, you know, have a parameter that can control the speed of the simulation. What if the user wants his simulation to be faster. He wants his delta t to be bigger. He wants it to be 10. He wants to multiply it by something. He wants to multiply it by 3 or 4 or anything to make it bigger. And surely, as we said, if your delta t is bigger, your simulation will be faster because you are regarding the duration between the two successive frames to be bigger. If that duration is 10 seconds between two frames, this is way fast, for example. So we are going to call this parameter the time scale. The time scale. Okay, so when the user makes the time scale bigger, he is going to multiply the delta t by a bigger number, and this will make the simulation faster. And remember the example of the car. When the delta t was 10 seconds, your car moved faster. You know, it moved a bigger distance. So if you remember this example, if your car moves from the first frame to the second frame, and the duration between these two frames is 10 seconds, it will move a bigger distance, so it will be faster. But if your delta t between the first and the second frame is 5 seconds, your car will move half of the distance, as we said, so it will move slower. Okay, and this is it. This is the formula of the time step. Okay, 1 multiplied by the time scale, or the time scale divided over the frame per seconds multiplied by the substeps. And this formula we are going to use in all of the simulations to update the velocity if we create custom forces. Sometimes in nodes like the gas threading and the gas turbulence, these nodes will add external forces to the velocity, and we'll talk about them. But sometimes they multiply this force by delta t, then they multiply it by the FPS also. Okay, so if we here in the formula multiply our delta t by FPS, this FPS will cancel this FPS. So what this means is that you are now not taking into consideration the real world time. So we divided by the FPS because we wanted our delta t to be in seconds when we had our delta t to be 1 over the FPS. This meant that we wanted to know how much or how many seconds between two successive frames. Okay, and if we are no longer dividing by the frame per second, this means that we moved from the second based calculations or the real time based calculations to only frame based calculations. So this means that if our time scale is 1 and our substep is 1, the delta t between the two successive frames will be 1. It's not here 1 second, it is 1 frame. Okay, Houdini now does not take into consideration that 24 frames form 1 second. In this calculation here, if we multiply the delta t by the FPS, and this here, if we use this formula, will make our force not dependent on the real time, and surely it will make the effect bigger because we are no longer dividing by 24, and the force effect will be bigger. Okay, and it will be added to the velocity, then added to the new velocity, because and this is frame based calculations. And if you try by numbers, our delta t was 1 over 24. If we multiply it by 24, our delta t is going to be 1. So now your force is going to be multiplied by 1, and this force will be added to the velocity. Before this, it was 1 over 24 multiplied by the force, then it was added to the velocity. So this is 24 times higher, and this will make the effect bigger. Actually, I don't know why they do this in some nodes, but maybe they want bigger force and they don't want the force to be affected by the real time in seconds. They want it to be a frame-based calculation. Whatever, this is an idea that I had to explain. Thank you for watching. So inside Houdini, if you create a DOP network, you will see here this time step, which is a time scale divided over the substep multiplied by the $FPS, which is the frame per second. And if you here open the global animation options, you will here have your FPS 24. And also you have the substeps here in the DOP network. Here you have the substeps to divide the time step into a number of substeps. And if you jump inside here, or for example, if you from here the shelf, you create a simple smoke simulation like this. And when you enter the DOP network here, you'll see in the pyro solver, you have the time scale, and you will have it in each node in Houdini. Okay, and you also in the DOP network have the scale time, which is a time scale. So you have here this time scale here controls this time step, and you have time scale in each node here. Okay, and also if you create a gas microsolver, for example, any gas microsolver like this gas disturb, you'll have this time scale also in it. And you here in the pyro solver also have the substepping option here, the minimum substep and the maximum substep in the solver itself. Okay, so I think now it's very clear what we have now. Thank you for watching.